In this video, we are going to understand how an integral controller first works as a standalone system, as a controller alone. How does the integrator behave? And then we are going to understand how does it react or how does it cooperate with the plant to maintain a stable output. If you have not watched a previous video in which I have stated the uh, different perspective of understanding an integral controller's functioning, I would recommend you to watch that video before coming into this, as I will be discussing some concepts which are taken as a reference from that video. First, let us consider a situation where I have a reference voltage of 12 and I have kept a constantly available voltage. I have kept this voltage deliberately at a constant. This should be actually my output voltage from a converter, but I have deliberately kept this constant at 11.75 volt. In that case, what will be the output of my integrator? We are going to study this scenario first. Now, what is the error here? The error is 0.25. We know that integrator keeps accumulating the area under the curve which is given as input to this. Now my input is a constant having amplitude or voltage of 0.25. This is my voltage, error voltage. This is across time. It is constantly having a value of 0.25 volt. If this is constantly in such a scenario, then the integrator should find the area under this curve at every instant, and if it is a continuous integrator, it will happen automatically, just like a capacitor, as I have already explained previously. And if it is a discrete integrator, we'll come to discuss about it. So now this will produce an output which will look something like this. It will be a ramp, and if I deliberately hold this at this value itself and I just keep waiting, the ramp will keep increasing, and it will go on be increasing forever. If I don't want such a thing to happen, if I want to saturate it something, or if I want to saturate it somewhere, that's how I bring a saturation block at its output. Whenever we use an integrator in a practical world, we will ensure that we put a saturation block at its output, because there may be a malfunction in the system. Your plant is not behaving properly, there has been some fault or something. In such a scenario, the integrator should not keep raising its value over a long period of time. It's not at all safe. So we saturate it. So when we saturate it, we say that, okay, you keep observing the value. If it is going more than some value, say for example, we are very much interested in employing this integrator in a buck converter, a power converter circuit. So it's essentially going to give us a duty ratio. So we say that you keep observing this value. Whenever this value is going greater than 1, you please saturate it there. You don't go further, you saturate it there. So that's how this saturator works. So even if we hold the input constant at 11.75 and it's constantly producing an output, technically the output of the integrator should be increasing forever, but since you are saturating it, it will be saturated here itself. This is how it works. Now moving on to the contrary part, assume that now my V0 is greater than V reference. If it is 12.25, then what will be my error? My error will be constantly negative. If it is constantly negative, the integrator will produce an output which will keep increasing in the negative direction. Which will keep increasing in the negative direction. I am giving a constant input of 0.25, so minus 0.25, so this is minus 0.25, this is my error voltage and this is my time. It is negative, this is origin, it is negative. The moment I give this, it will keep accumulating it in the opposite direction, right? So this will keep continuing again and again. Now when you come to a power converter, we say that my duty ratio is the output of the integrator and we tend to saturate it. So what is the lower value of the duty ratio? We know that duty ratio ideally can lie between 0 and 1. So what is the lower value of duty ratio? Duty ratio can never go below a value of 0. So we say that whenever your output is going below 0, you better hold it there. Hold it at 0 itself. Don't go further. So that's also saturation. So how a system will essentially look is, whenever you have an integrator, if this is your integrator block, at its output, if this is the input to the integrator block, the feedback system, and this is the output, you will inherently have a saturation. And in this saturation block, you will say what is the minimum value and what is the maximum value to which this output can go. If this output is exceeding the maximum value, it will hold at the maximum value. If this output is going below the minimum value, it will hold at the minimum value. Whenever an integrator is used in the feedback system for controls, we should always ensure that saturation is available. If saturation is not available, as I said earlier, if your system becomes faulty, if a plant becomes faulty due to some malfunctioning, the value of the integrator will shoot up like anything. Now, this is the standalone behavior of an integrator. Now let us come to a situation where there's a plant with me, right? Now, I am giving 24 volt to this plant. Assume that the plant's output is initially 0. This plant is nothing but my synchronous buck converter or buck converter, or for that matter any power converter, right? The initial value is 0. Initially the value is 0. What is my reference value? It's 12 volt. What will be my error? It will be very large. It will be 12 minus 0, it will be 12. Now my integrator will integrate that whole value and it will give a duty ratio appropriately, and the duty ratio will be very high. It will be very high and it will drive this. So because of that high duty ratio, we know that plant is nothing but V naught equals to D into V in. So since this is very high and this is fixed, V in is fixed and D is very high, your V naught will drastically start increasing from 0 to 5 volt to 7.5 volt, and it will shoot up. It will shoot up and it will go up to what level? Up to maybe 13 volt or 15 volt. It will go up to 15 volt, but the moment this become 15 volt, the 15 volt will come here. Is no longer 12, 15, sorry. This no longer is 12, this is 15, and this error has now become negative. Has become minus 3. Now this integrator will pull down the duty ratio. It will pull down the duty ratio like anything, and it will come down to maybe 11.5 volt. And then it will again see, okay, now this is 11.5 volt here, it's not 15 volt, it's not minus 3. Now we have an error of plus 0.5. And that plus 0.5 will slightly increase the duty ratio. So your 11.5 will slightly increase to 12.25. You have to understand here that what my integral controller or integrator is actually doing. If I am having a reference voltage, okay, if I am having a reference voltage, initially it was 0, it shot up, then it came down, again it shot up, then it came down, and it will try to maintain the output of the plant around this value. It will go up, the error will become positive, it will come down. Again it will pull down more than necessary, the error will become negative, it will again pull up. Again, it will pull up more than necessary, the error will become negative, it will again pull down. So this is the action of integrator. This is how an integrator functions with any plant. Here we are talking about a power converter. Let it be any plant. Any plant, when controlled by an integrator, will essentially do only this. So how is it reducing the steady state error? We already discussed in the first video. How is it reducing the steady state error? You could see that the steady state error here is 0 because it is always either going slightly above reference or slightly coming down. It is either going slightly up or slightly down. It's always around reference. Its mean value will definitely be around reference. So this explains the action of an integrator.